I get asked about this question every single semester. Part A sounds difficult, but it's really pretty easy. What they're saying is they're saying that if RH is equal to 1.097 times 10 to the 7th inverse meters, what is the value of RH in joules? But they're asking you to do it symbolically using algebra. They're wanting you to solve for this variable RH in terms of Planck's constant, right? That's Planck's constant, and that's the speed of light. What we're going to do is the easiest way to do this is to state what we already know. What facts do we already know? We already know that the inverse of wavelength equals RH times 1 over n squared final minus 1 over n squared initial. We also know that the speed of light is equal to wavelength times frequency, and we know that energy is equal to Planck's constant times frequency. What are the common things that link all these equations? Well, these two are linked by wavelength, and these two are linked by frequency. Let's combine these two equations. Whenever we combine these two equations and we want to solve them for energy, we always go through frequency. So what I'm going to do is I'm going to come over here and I'm going to solve my speed of light equation for frequency. And frequency is equal to the speed of light divided by wavelength. I'm then going to substitute in to my energy equation, and that's going to give me energy is equal to Planck's constant times the speed of light divided by wavelength. Hey, I've got an inverse wavelength. Let's make it abundantly clear. Energy is equal to Planck's constant times the speed of light times, because we're dividing by wavelength, we're really multiplying by the inverse, right? So we now know that energy is equal to Planck's constant divided by the inverse of energy. Okay. So now we can do another substitution. Right? If 1 over wavelength is equal to RH, 1 over inverse is equal to all this according to that equation, right? We can substitute in for that inverse wavelength. And that gives us energy is equal to Planck's constant times the speed of light times RH times 1 over n squared f minus 1 over n squared initial. Pull out terms. pull out terms, and that gives me energy is equal to Planck's constant times the speed of light times RH. And we can do this because multiplicative is commutative. So what does this show us? Well, look at what we have right here. We learned in lecture that the change in energy is equal to the joules value. We'll make that in joules. Therefore, where our RH value right here is in meters, here, we'll do it like this. The Rydberg constant in joules, therefore, has to be equal to Planck's constant times the speed of light times the Rydberg constant in inverse meters. And we can actually prove that. Remember, I gave you the value of the Rydberg constant in terms of energy in class or in lecture. So our joules equals Planck's constant, 6.626 times 10 to the negative 34th joules seconds, times our speed of light, times 10 to the 8th meters per second, times 1.097, and we're going to be gracious enough to accept their meter value rather than go through that little quick derivation ourselves, since they gave it to us in the problem. 10 to the positive 7th inverse meters. We multiply all that together, and guess what? We get that exact same value I gave you in lecture. RH in joules is 2.179 times 10 to the negative 18 joules. All right, now let's take a look at part 2, which has kind of gotten buried here. And before we move to part 2, write down this value. I gave it to you in lecture and told you to write it down. It's necessary for part 2 and will save you time. All right, let's take a look at part 2. Part 2 here is a much more straightforward example like you're used to. In part 2, they're asking, what is the change in energy in those annoying units of kilojoules per mole for an electron transition from n equals 3 to n equals 2? Thanks to what we just derived and thanks to what we've done in lecture, we know that the difference in energy for an electron transitioning between two energy states is equal to the negative RH value times 1 over final squared minus 1 over initial squared, where the RH value is 2.179 times 10 to the negative 18 joules when we're using that energy-based formula. So now it's just a matter of plug and chug with a cutesy finishing step to follow. So we've got our delta E equals a negative 2.179 times 10 to the negative 18 joules times, it's going from 3 to 2, so 2 squared minus 3 squared. Plug that all into our calculator. watch your parentheses, watch your inverses. 4 inverse minus 9 inverse equals 0.1388 times 2.179 exponent negative 18 equals a negative 3.026 times 10 to the negative 19th joules. This is for 1 electron. They want it per a mole of electrons. So we're going to have to do another cutesy finishing step because that's kilojoules per, that's joules per an electron. So we're going to have to get it to kilojoules per a mole. Well, there are, we want it per mole, so we're going to place moles where they're on the bottom, electrons where they'll cancel out. We know that there are 6.022 times 10 to the 23rd electrons in 1 mole of electrons. Then we have joules. We want to place joules where they cancel out. We want kilojoules. Multiply everything on top, divide through by everything on the bottom. I don't know if you can hear it, but I've got 2 kids in the background playing pirates, and it's a more than a little bit distracting. And let me tell you, one of the pirates is very tyrannical. That is the answer I would want. They may want it only in positive form. Let me check on that for a second. They do want it negative. So there's your answer. Beep.